Mobile mixer unit yield and within batch uniformity.
Let's move on to the procedure for conducting a yield test. Now, in order to minimize the amount of concrete we need to produce to achieve this task, we could limit the volume to something of the order of a quarter cubic meter. So if we were to continue with our 30 MPa mix that we used to calibrate our unit, our counter set point would be 1/4 of what we calculated, or 0.25 times of 533 counts, which should give us a counter set point of about 133 counts. However, we're going to need to run within batch uniformity testing, as well as securing concrete test cylinders for compressive strength testing and hardened air void analysis. So we might as well select a mix that we can use to cover all elements of the certification process. To that end, we're going to want to select a mix to produce a CSA Class C2 exposure mix with a design strength of 32 MPa at 28 days, air entrained 5 to 8% with a target slump in the order of 80 to 100 millimeters, plus or minus 30 millimeters. If you don't have one of those designs readily available, please contact the consultant who certified your aggregates, who will most likely be able to provide you with a starting point. Knowing the flow rates of your materials based on the calibrations you've just conducted, you should be able to determine your counter set point to produce a quarter cubic meter based on the cement content with all the corresponding aggregate gate settings and admixture and water dispensing rates that go along with it. But before we batch any concrete, we'll need to build a yield box of precise known volume. In no case shall the volume of the container be less than 0.2 cubic meters. Regardless of the container volume, the volume of the concrete obtained during the yield test shall be within plus or minus 1.3% of the volume of the container. In this example, we're proposing to build a quarter cubic meter box to fill with concrete. The dimensions will be 1 meter wide by 1 meter long by 0.25 meters deep and could be fabricated out of good quality spruce and plywood. It may be wise to make the form detachable from the base for unmolding and cleanup purposes following the test. It should also be sturdy enough to withstand multiple use without distortion in dimensions or volume. Now that we've got our yield box built, let's get our mobile mixer charged with materials, run our moistures on our aggregates, and enter the figures into the onboard computer and make sure our aggregate gate and water and admixture dispenser settings are all adjusted for the new C2 mix design that we're going to run. We should ensure that our admixtures are set to dispense at the correct rates to attain our target slump and air contents, and that our water dispensing rate will not exceed a moisture-corrected water to cementing materials ratio of 0.45 as mandated for a Class C2 exposure mix. For example, if our mix design has 400 kilograms of cement per cubic meter and the mobile mixer unit is dispensing cement at a rate of 0.6 kilograms per count as determined from our baseline calibration, that means the water dispensing rate needs to be set so that the total water in the mix dispensed from the water tank plus any excess water available from the aggregates that can combine with the cement does not exceed a water to cementing materials ratio of 0.45. In a perfect world where all the sand and stone is perfectly saturated with no excess or shortfall of moisture, that would mean just setting the water dispensing rate to a maximum of 0.6 kilograms per count times 0.45, which would equal 0.27 kilograms of water per count. But we know that sometimes the rock and sand are a little bit on the dry side or a little bit on the wet side. That's why we say not to use sand and rock that are excessively dry or excessively wet. It's also why we run moisture contents on the aggregates as we charge the bins of our mobile mixer so that we can determine if our aggregates are overall on the dry side, where they're going to want to absorb some of that mixed water that we put in, or whether they're on the wet side where they're going to contribute some water to the mix, and in that case we would need to hold a little bit of water back to ensure we don't exceed that 0.45 water to cementing materials ratio. Most modern mobile mixer units have the software on board to adjust the mix design provided the moisture contents, absorption rates, and densities of the aggregates are entered into the system prior to batching any concrete. If the unit being certified does not have this feature on board, you can do the moisture correction calculations manually. Once again, moisture correction calculations can be found in Design and Control of Concrete Mixtures, published by the Cement Association of Canada. In the case of our admixtures, the dosage rates are usually set based upon the cement weight, but are very specific to the brand and type of admixtures that you're using. You'll need to get the recommended dosage rates from your admixture supplier. The dosing rate of most common admixtures is in milliliters per 100 kilograms of cementing materials. For example, a normal range water reducer, which most concrete producers use and usually results in about a 10% water reduction, might be recommended by the admixture manufacturer to be dosed at a rate of about 250 mils per 100 kilograms of cementing materials, or in other words, 2.5 milliliters per kilogram. Once again, from the calibration process, we learned that our cement dispenses at a rate of 0.6 kilograms per count. Knowing the cement dispensing rate and the manufacturer's recommended dose for the water reducer of 2.5 mils per kilogram of cementing materials, we can calculate that the mobile mixer admixture dispenser is contributing 2.5 mils per kilogram times 0.6 kilograms of cementitious materials per count, which equals 1.5 mils per count. Air entrainment admixtures dosage rates are usually of the order of something less than 100 mils per 100 kilograms of cementing materials. Again, ask your admixture supplier for a dosage rate. Let's use the example of a dosage rate of 50 mils per 100 kilograms of cement. That would mean 0.5 mils per kilogram of cement dispensed. Again, from your baseline cement rate of 0.6 kilograms per count that you determined during your calibration, the rate of admixture dispensed should be 0.5 mils times 0.6 kilograms per count of cement, which equals 0.3 mils per count. Now that we've got all of our materials dispensing rates calculated and set, let's start making concrete. Start up the unit and discharge concrete until a continuous uniform concrete mix within the selected target and slump range is established. Then pass a sampling device through the discharge stream to collect a minimum 25-liter representative grab sample. Stop the conveyor and auger. If a chute is used, it should be completely emptied. The auger must remain full. Allow the sample to stand for 4 minutes, protecting it from sun, wind, sources of rapid evaporation, and from contamination. Run slump and air tests to confirm the concrete is well within the desired range for these two parameters. If it's not, adjust the design and repeat the previous steps, securing an additional sample to confirm the desired slump and air. Once the concrete is confirmed to be in the desired slump and air range, conduct a density test and immediately cast 5 100 by 200 millimeter cylindrical concrete test specimens from the most recently collected and corresponding representative sample. Set the counter to 0 and discharge concrete into the quarter cubic meter yield box until the count that corresponds to the volume of the yield box is reached. Level off the surface of the concrete without removing any concrete from the yield box. The yield is considered to be acceptable if the concrete surface is within plus or minus 1.3%, in this case within plus or minus 3 millimeters of the top of the yield box when the air content is between 5 and 8%, and the slump is within the specified range of the selected target, for example, 90 plus or minus 30 millimeters. Once yield is confirmed to be acceptable, we can proceed to conduct the within-batch uniformity test. Restart the mixer and continue to run at the established settings and collect 2 additional representative samples spaced at least a half a meter of production volume apart. Allow each sample collected to stand for 4 minutes and immediately run slump, air, and density tests. Compare results for slump, air, and density from each sample to determine if they're within batch tolerances defined in CSA A23.1, clause 5.2.4.5.2.1. If they're not within the tolerance limits, continue to collect additional samples at the same spacing interval until 3 consecutive samples collected are within the specified tolerances. If materials inventories become exhausted as a result of this process, recharge the bins and tanks, confirm the moisture contents of the aggregates, and repeat the entire yield test and within batch uniformity process until conformity with the standard and this audit checklist procedure are confirmed. The 5 concrete cylindrical test specimens cast to represent the concrete produced that passed the yield and within batch uniformity tests should be handled and cured in accordance with CSA A23.2-3C. All test specimens cast should be tested by a third-party certified independent concrete test laboratory to determine average compressive strength of 2 cylinders at age of 7 days and 2 at the age of 28 days. The 5th cylinder cast shall be reserved to conduct hardened air void analysis, confirming the concrete produced is within air content, air void spacing, and specific surface limits for Class C2 exposure concrete. All field tests shall be conducted and concrete test cylinders shall be cast by a certified testing technician in the presence of the auditor at the time of the audit and collected by the auditor's lab the day following the audit.